Rainbow from Wikipedia, the free encyclopedia. For other uses, see rainbow disambiguation. A rainbow is a meteorological phenomenon that is caused by reflection, refraction, and dispersion of light and water droplets, resulting in a spectrum of light appearing in the sky. It takes the form of a multicolored circular arc. Rainbows caused by sunlight always appear in the section of sky directly opposite the sun. Rainbows can be full circles, however, the observer normally sees only an arc formed by illuminated droplets above the ground and centered on a line from the sun to the observer's eye. In a primary rainbow, the arc shows red on the outer part and a violet on the inner side. This rainbow is caused by light being refracted when entering a droplet of water, then reflected inside on the back of the droplet and refracted again when leaving it. In a double rainbow, a second arc is seen outside the primary arc and has the order of its colors reversed, with red on the inner side of the arc. This is caused by the light being reflected twice on the inside of the droplet before leaving it. Overview. A rainbow is not located at a specific distance from the observer, but comes from an optical illusion caused by any water droplets viewed from a certain angle relative to a light source. Thus, a rainbow is not an object and cannot be physically approached. Indeed, it is impossible for an observer to see a rainbow from water droplets at any angle other than the customary one of 42 degrees from the direction opposite the light source. Even if an observer sees another observer who seems under or at the end of a rainbow, the second observer will see a different rainbow farther off at the same angle as seen by the first observer. Rainbows span a continuous spectrum of colors. Any distinct bands perceived are an artifact of human color vision, and no banding of any type is seen in a black and white photo of a rainbow. Only a smooth gradation of intensity to a maximum, then fading towards the other side. For colors seen by the human eye, the most commonly cited and remembered sequence is Newton's sevenfold red, orange, yellow, green, blue, indigo, and violet, remembered by the mnemonic Richard of York gave battle in vain. Boy, Roy, Roygbiv. Rainbows can be caused by many forms of airborne water. These include not only rain, but also mist, spray, and airborne dew. Visibility. Rainbows can be observed whenever there are water droplets in the air and sunlight shining from behind the observer at a low altitude angle. Because of this, rainbows are usually seen in the western sky during the morning and in the eastern sky during the early evening. The most spectacular rainbow displays happen when Half the sky is dark with raining clouds, and the observer is at a spot with clear sky in the direction of the sun. The result is a luminous rainbow that contrasts with the darkness background. During such good visibility conditions, the larger but fainter secondary rainbow is often visible. It appears about 10 degrees outside of the primary rainbow with inverse order of colors. The rainbow effect is also commonly seen near waterfalls or fountains. In addition, the effect can be artificially created by dispersing water droplets into the air during a sunny day. Rarely, a moonbow, lunar rainbow, or nighttime rainbow can be seen on strongly moonlight nights, as human visual perception for color is poor in low light. Moonbows are often perceived to be white. It is difficult to photograph the complete semi-color of a rainbow in one frame, as this would require an angle of view of 84 degree for a 35 mm camera. A wide-angle lens with a focal length of 19 mm or less would be required. Now that software for stitching several images into a panorama is available. Images of the entire arc and even secondary arcs can be created fairly easily from a series of overlapping frames. From above the Earth, such as in an aeroplane, it is sometimes possible to see a rainbow as a full circle. This phenomenon can be confused with a glory phenomenon, but a glory is usually much smaller, covering only 5 through 20 degrees. The sky inside a primary rainbow is brighter than the sky outside of the bow. This is because each droplet is a sphere and it scatters light over an entire circle disk in the sky. The radius of the disk depends on the wavelength of light, with red light being scattered over a large angle, then blue light over most of the disk. Scattered light at all wavelengths overlaps, resulting in white light which brightens the sky. At the edge, the wavelength dependence of the scattering gives rise to the rainbow. Light at primary rainbow arc is 96% polarized, tang- tangential to the arc. Light of second arc is 90% polarized. Number of colors in spectrum of rainbow. A spectrum obtained using a glass prism and a point source is a continuum of wavelengths without bands. The number of colors that the human eye is able to distinguish is a spectrum in a spectrum is in the order of 100. according to according accordingly the Munsell color system, a 20th century system for numerically describing colors based on equal steps for human visual perception, distinguishes 100 hues. The apparent discreteness of main colors is an artifact of human perception, and the exact number of main colors is a somewhat arbitrary choice. Um, Red, orange, yellow, green, blue, indigo, violet. Newton, who admitted his eyes were not very critical in distinguishing colors, originally 1672, divided the spectrum into five main colors: red, yellow, green, blue, and violet. Later, he included orange and indigo giving seven main colors by analogy to the number of notes in a musical scale. Newton chose to divide the visible spectrum into seven colors out of a belief derived from the beliefs of the ancient Greeks sophists who thought there was a connection between the colors, the musical notes, the known objects in the solar system, and the days of the week. Scholars have noted that what Newton regarded at the time as blue would today be regarded as a cyan, and what Newton called indigo would today be considered blue, red, orange, yellow, green, cyan, blue, violet. According to Isaac Asimov, it is customary to list indigo as a color lying between blue and violet, but it has never seemed to me that indigo is worth the dignity of being considered a separate color. To my eyes, it seems merely deep blue. The color pattern of a rainbow is different from a spectrum, and the colors are less saturated. There is spectral smearing in a rainbow owing to the fact that for any particular wavelength there is a distribution of exit angles rather than a single unvarying angle. In addition, a rainbow is a blurred blurred version of the bow obtained from a point source, because the disk diameter of the sun 0.5 degrees cannot be neglected compared to the width of a sun of a rainbow 2%. Further red of the first supplementary rainbow overlaps the violet of the primary rainbow. So rather than the final color being a variant of spectral violet, it is actually a purple. The number of color bands of a rainbow may therefore be different from the number of bands in a spectrum, especially if the droplets are particularly large or small. Therefore, the number of colors of a rainbow is variable. If, however, the word rainbow is used inaccurately to mean spectrum, it is the number of main colors in the spectrum. The question of whether everyone sees seven colors in a rainbow is related to the idea of linguistic ling, linguistic relativity. Suggestions have been made that there is universality in the way that rainbow is perceived. However, more recent research suggests that the number of distinct colors observed and what these are called depend on the language that one uses, with people whose language has fewer color words seeing fewer discrete color bands. Explanation: when sunlight encounters a raindrop, part of the light is reflected and the rest enters the raindrop. The light is refracted on the surface of the raindrop. When this light hits the back of the raindrop, some of it is reflected off the back. When the internally reflected light reaches the surface again once more, some is internally reflected and some is refracted as it exits the drop. The light that reflects off the drop exits from the back or continues to bounce around inside of the drop after the second encounter with the surface is not relevant to the formation of the primary rainbow. The overall effect is that part of the incoming light is reflected back over the range of 0 to 42% with the most intense light at 42%. This angle is independent of the size of the drop, but does depend on its refractive index. Seawater has a higher refractive index than rainwater, so the radius of a rainbow in sea spray is smaller than a true rainbow. This is visible to the naked eye by misalignment of those bows. The reason the returning light is most intense at about 42% is that this is a turning point. Light hitting the outermost ring of the drop gets returned at less than 42%, as does the light hitting the drop nearer to its center. There is a circular band of light that all gets returned right around 42%. If the sun was a laser emitting parallel monochromatic rays, then the luminance brightness of the bow would tend toward infinity at this angle, ignoring interference efforts. See caustic optics. But since the sun's luminance is infinite and its rays are not all parallel, it covers about half a degree of the sky. The luminance does not go to infinity. Furthermore, the amount by which light is refracted depends upon its wavelength and hence its color. This effect is called dispersion. Blue light, softer wavelength, is refracted at a greater angle than red light, but due to the reflection of light rays from the back of the droplet, the blue light emerges from the droplet at a smaller angle to the original incident white light ray than the red light. Due to this angle, blue is seen on the inside of the arc of the primary rainbow and red on the outside. The result of this is not only to give different colors to different parts of the rainbow, but also to diminish the brightness. A rainbow formed by droplets of a liquid with no dispersion would be white, but brighter than a normal rainbow. The light at the back of the rainbow raindrop does not undergo total internal reflection, and some light does emerge from the back. However, light coming out the back of the raindrop does not create a rainbow between the observer and the sun because spectra emitted from the back of the raindrop do not have a maximum of intensity as the other visible rainbows do, and thus the colors blend together rather than forming a rainbow. A rainbow does not exist at one particular location. Many rainbows exist. However, only one can be seen depending on the particular observer's viewpoint. As droplets of light illuminated by the sun, all raindrops refract and reflect the sunlight in the same way, but only the light from some raindrops reach the observer's eye. The observer's eye. This light is what constitutes the rainbow for that observer. The whole system composed by the sun's rays, the observer's head, and the spherical water drops has an axial symmetry around the axis through the observer's head and parallel to the sun's rays. The rainbow is curved because the set of all the raindrops that have the right angle between the observer, the drop, and the sun lie on a cone pointing at the sun with the observer at the tip. The base of the cone forms a circle at an angle of 40 through 2% to the line between the observer's head and their shadow, but 50% or more of the circles below the horizon, unless the observer is sufficiently far above the Earth's surface to see it at all. For example, in an aeroplane, see above. Alternatively, an observer with the right vantage point may see may see the full circle in a fountain or waterfall spray. Mathematical derivation. It is possible to determine the perceived angle which the rainbow subtends as follows. Given a spherical raindrop and defining the perceived angle of the rainbow as 2 something and the angle of the internal reflection as 2b, then the angle of 2q and the angle of the internal reflection as 2b, then the angle of incident of the sun's rays with respect to the drop's surface normal is 2b through q. Since the angle of refraction is b, Snell's law gives us sin 2b through q equals n sin b, where n equals 1.333 is the refractive index of water. Solving for q, we get q equals 2b through r sin n sin b. The rainbow will occur where the angle q is maximum with respect to the angle b. Therefore, from calculus, we can set dq / db equals 0 and solve for b, which yields b max equals cos minus 1 to check or pi, whatever that is, -1 plus n2 on over pi or check 3n equals to 40.2 per degrees. Substituting back into the earlier equation for q yields 2q max equal to 42 degrees as the radius angle of the rainbow. Variations. Double rainbows. Double rainbow redirects here for other uses. See double rainbow. The term double rainbow is used when both the primary and secondary rainbows are visible. In theory, all rainbows are double rainbows, but since the secondary rainbow is always fainter than the primary, it may be too weak to spot in practice. Secondary rainbows are caused by a double reflection of sunlight inside the water droplets. Technically, the second rainbow is centered on the sun itself, but since its angular size is more than 90%, about 127% for violet to 130% for red. It is seen on the same side of the sky as the primary rainbow, about 10 degrees outside it at an apparent angle of 50 through 53 degrees. As a result of the inside of the secondary rainbow being up to the observer, the colors appear reversed compared to those of the primary bow. The secondary rainbow is fainter than the primary because more light escapes from two reflections compared to one, and because the rainbow itself is spread over a greater area of the sky. Each rainbow reflects white light inside its colored bands, but that is down for the primary and up for the secondary. The dark area of unlit sky lying between the primary and secondary bows is called Alexander's band, after Alexander of Asphodisias, who first described it. Twinned rainbows. Unlike a double rainbow that consists of two separate and concentric rainbow arcs, the very rare twinned rainbow appears as two rainbow arcs that split from a single base. The colors in the second rainbow of the second bow, rather than reversing as in a secondary rainbow, appear in the same order as the primary rainbow. A normal secondary rainbow may be present at all. Twin rainbows can look similar too, but should not be confused with supernumerary bands. The two phenomena may be told apart by their difference in color profile. Supernumerary bands consist of subdued pastel hues, mainly pink, purple, and green, while the twinned rainbow shows the same spectrum as a regular rainbow. The cause of a twin rainbow is the combination of different sizes of water drops falling from the sky due to air resistance. Raindrops flatten as they fall, and flattening is more prominent in larger water drops. When two rainbow rain showers with different sized raindrops combine, they each produce slightly different rainbows, which may combine and form a twinned rainbow. A numerical ray tracing study showed that a twin rainbow on a photo could be explained by a mixture of 0.40 and 0.45 mn droplets. That small difference in droplet size resulted in a small difference in flattening of the droplet shape and a larger difference in flattening of the rainbow top. Meanwhile, the even rarer case of a raindrop rainbow split into three branches was observed and photographed in nature. Full circle rainbow. In theory, every rainbow is a circle, but from the ground. Usually, only its upper half can be seen, since the rainbow center is diametrically opposed to the sun's position in the sky. More of the circle comes into view as the sun approaches the horizon. Meanwhile, meaning that the largest section of the circle normally seen is about 50% during sunset or sunrise. Viewing the rainbow's lower half requires the presence of water droplets below the observer's horizon, as well as sunlight that is able to reach them. These requirements are not usually met when the viewer is at a ground level, either because droplets are absent in the required position, or because the sunlight is obstructed by the landscape behind the observer. From a high viewpoint, such as a high building or an aircraft, however, the requirements can be met and the full circle rainbow can be seen. Like a partial rainbow, the circle rainbow can have a secondary bow or supernumerary bows as well. It is possible to produce the full circle when standing on the ground, for example, by spraying a water mist from a garden hose while facing away from the sun. A circular rainbow should not be confused with the glory, which is much smaller in diameter and is created by different optical processes in the right circumstances. A glory and a circular rainbow or fog bow can occur together. Another atmospheric phenomenon that may be mistaken for a circular rainbow is the 22% halo, which is caused by ice crystals rather than liquid water droplets and is located around the sun or moon, not opposite it. Supernumerary rainbows. It in certain circumstances, one or several narrow, faintly colored bands can be seen bordering the violet edge of a rainbow. Example, inside the primary bow or much more rarely outside the secondary. These extra bands are called supernumerary rainbows or supernumerary bands. Together with the rainbow itself, the phenomenon is also known as a stacker rainbow. The supernumerary bows are slightly detached from the main bow, become successively fainter along with their distance from it, and have pastel colors consisting mainly of pink, purple, and green hues rather than the usual spectrum pattern. The effect becomes apparent when water droplets are evolved that have a diameter of about 1 mm or less. The smaller the droplets are, the broader the supernumerary bands become, and the less saturated their colors. Due to their origin in small droplets, supernumerary bands tend to be particularly prominent in fog bows. Supernumerary bows cannot be explained using classical geometric optics. The alternating faint bands are caused by interference between rays of light following slightly different paths with slightly varying lengths within the raindrops. Some rays are in phase, reinforcing each other through constructive interference, creating a bright band. Others are out of phase by up to half a wavelength, canceling each other out through destructive interference and creating a gap, giving the different angles of refraction for rays of different colors. The patterns of interference are slightly different for rays of different colors. So each bright band is differentiated in color, creating a miniature rainbow. Supernumerary rainbows are clearest when raindrops are small and of ununiform size. The very existence of supernumerary rainbows was historically a first indication of the wave nature of light, and the first explanation was provided by Thomas Young in 18 04. Reflective rainbow, reflection rainbow. When a rainbow appears above a body of water, two complementary mirror bows may be seen below and above the horizon, originating from different light paths. Their names are slightly different. A reflected rainbow may appear in the water surface below the horizon. The sunlight is first deflected by the raindrops and then reflected off the body of water before reaching the observer. The reflected rainbow is frequently visible, at least partially, even in small puddles. A reflection rainbow may be produced where sunlight reflects off a body of water before reaching the raindrops. If the water body is large, quite over, quite, quite over its entire surface and close to the rain curtain, the reflection rainbow appears above the horizon. It intersects the normal rainbow at the horizon, and its arc reaches higher in the sky, with its center as high above the horizon as the normal rainbow center is below it. Due to the combination of requirements, a reflection rainbow is rarely visible. Of the eight separate bows may be distinguished if the reflected and reflection rainbows happen to occur simultaneously. The normal non-reflection primary and secondary bows above the horizon 1, 2 with their reflected counterparts below it 3, 4, and the reflection primary and secondary bows above the horizon 5, 6 with the reflected counterparts below it 7, 8. Monochrome rainbow. Main article: monochrome rainbow. Occasionally, a shower may happen at sunrise or sunset where the shorter wavelengths, like blue and green, have been scattered and essentially removed from the spectrum. Further scattering may occur due to the rain, and the result can be the rare and dramatic monochrome or red rainbow. Higher order rainbows. In addition to the common primary and secondary rainbows, it is also possible for rainbows of higher orders to form. The order of a rainbow is determined by the number of light reflections inside the water droplets that create it. One reflection results in the first order or primary rainbow. Two reflections create the second order or secondary rainbow. More internal reflections cause bows of higher orders, theoretically unto infinity, as more and more light is lost with each internal reflection. However, each subsequent bow becomes progressively dimmer and therefore increasingly harder to spot. An additional challenge is observing the third order or tertiary, a fourth order quaternary rainbows is their location and the direction of the sun, about 40% and 45% from the sun, respectively, causing them to become drowned in its glare. For these reasons, naturally occurring rainbows of an order higher than 2 are rarely visible to the naked eye. Nevertheless, sightings of the third order bow in nature have become reported, and in 2011 it was photographed definitely for the first time. Shortly after, the fourth order rainbow was photographed as well, and in 2014 the first ever pictures of the fifth order or quinary rainbow located located in between the primary and secondary bows were published. In a laboratory setting, it is possible to create bows of much higher orders. Felix Billet, 1808 through 1882, depicted angular positions up to the 19th order rainbow, a pattern he called a rows of rainbows. In the laboratory, it is possible to observe higher order rainbows by using extremely bright and well collimated light producers by lasers. Up to the 200th order rainbow was reported by NGETAL in 1998 using a similar method by an orgone ion laser beam. Tertiary and quaternary rainbows should not be confused with triple and quadruple rainbows, terms sometimes erroneously used to refer to the much more common supernumerary bows and reflection rainbows. Rainbows under moonlight. Main article: Moonbow. Like most atmospheric optical phenomena, rainbows can be caused by light from the sun, but also from the moon. In case of the latter, the rainbow is referred to as a lunar rainbow or moonbow. They are much dimmer and rarer than solar rainbows, requiring the moon to be near full in order for them to be seen. For the same reason, rainbows are often perceived as white and may be thought of as monochrome. The full spectrum is present, however, but the human eye is not normally sensitive enough to see the colors. Long exposure photographs will sometimes show the color in this type of rainbow. Fogbow. Main article: Fogbow. Fogbows form in the same way as rainbows, but they are formed by much smaller cloud and fog droplets that diffract light extensively. They are almost white with faint reds on the outside of the blue and blues inside. Often one or more broad supernumerary bands can be discerned inside the inner edge. The colors are dim because the bow is in each color is very broad and the colors overlap. Fog bows are commonly seen over water when air is contact with the cooler water is chilled, but they can be found anywhere in the fog. In fog in thin enough for the sun to shine through, and the sun is fairly bright. They are very large, almost as big as a rainbow and much broader. They sometimes appear with a glory at the bow's center. Fog bows should not be confused with ice halos, which are very common around the world and visible much more often than rainbows of any order, and yet are unrelated to rainbows. Circumhorizontal and circumzenithal arcs. The circumzenithal and circumhorizontal arcs are two related optical phenomena similar in appearance to a rainbow, but unlike the latter, their origin lies in light refraction through hexagonal ice crystals rather than liquid water droplets. This means that they are not rainbows, but members of the large family of halos. Both arcs are brightly colored ring segments centered on the zenith, but in different positions in the sky. The circumzenithal arc is notable, curved, and located high above the sun or moon, with its convex side pointing downwards, creating the impression of an upside down rainbow. The circumhorizontal arc runs much closer to the horizon, is more straight, and located at a significant distance below the sun or moon. Both arcs have their red side pointing towards the sun, and their violet part away from it, meaning the circumzenithal arc is red on the bottom, while the circumhorizontal arc is red on top. The circumhorizontal arc is sometimes referred to by the misnomer five rainbow in order to view it. The sun or moon must be at least 58 degrees above the horizon, making it a rare occurrence at higher altitudes. The circumzenithal arc, visible only at a solar or lunar elevation of less than 32%, is much more common, but often missed since it occurs almost directly overhead. Rainbows on Titan. It has been suggested that rainbows might exist at Saturn's moon Titan, as it has a wet surface and humid clouds. The radius of a Titan rainbow would be about 49% instead of 42% because the fluid is that cold. That cold environment is methane instead of water. Although visible rainbows may be rare due to Titan's hazy skies, infrared rainbows may be more common, but an observer would need infrared night vision goggles to see them. Rainbows with different materials. Droplets or spheres composed of materials with different refractive indices than plain water produce rainbows with different radius angles. Since salt water has a higher refractive index, a sea spray bow doesn't perfectly align with the ordinary rainbow if seen at the same time. Tiny plastic or glass marbles may be used in road marking as a reflectors to enhance its visibility by drivers at night due to a much higher refractive index. Rainbows observed on such marbles have a noticeable smaller radius. One can easily produce such phenomena by sprinkling liquids of different refractive indices in the air as illustrated in the photo. The displacement of the rainbow due to different refractive indices can be pushed to a peculiar limit. Peculiar limit. For a material with a refractive index larger than 2, there is no angle fulfilling the requirements for the first order rainbow. For example, the index of refraction of a diamond is about 2.4, so diamond spheres would produce rainbows starting from the second order, omitting the first order in general, as the refractive index exceeds a number n plus 1, where n is a natural number and the critical incidence angle for n times internally refracted rays escapes the domain 0, comma pi 102. This results in a rainbow of the nth order striking to the anti-solar point and vanishing. Um, Scientific history. The classical Greek scholar Aristotle 384 through 322 BC was first to devote serious attention to the rainbow. According to Raymond L. Lee and Alistair B. Fraser, despite its many flaws and its appeal to Pythagorean numerology, Aristotle's qualitative qualitative explanation showed an inventiveness and reflective consistency that was unmatched for centuries. After Aristotle's death, much rainbow theory consisted of refraction to his work, although not all of this was uncritical. In Book 1 of Naturalis Quaestiones, c. 65 AD, the Roman philosopher Seneca the Younger discusses various theories of the formation of rainbows extensively, including those of Aristotle. He noticed that rainbows appear always opposite to the sun, that they appear in water spraying by a rower, in the water spat by a fuller, on clothes stretched on pegs, or by water sprayed through a small hole in a burst pipe. He even speaks of rainbows produced by small rods, virgulae of glass, anticipating anticipating Newton's experiences with prisms. He takes into account two theories: one, that the rainbow is produced by the sun reflecting it each water drop; the other, that it produced by the sun reflected in a cloud shaped like a concave mirror. He favors the latter. He also discusses other phenomena related to rainbows: the mysterious Virgae rods, halos, and perhelia. According to Hussein Ghazi Topdemir, the Arab physicist and polymath Ibn al-Gaytham al-Hazan 965 through 1039 attempted to provide a scientific explanation for the rainbow phenomenon. In his Maqala Fi al-Hala WAQAWS on the rainbow and halo, A.L. Haytham explained the formation of rainbow as an image which forms at a concave mirror. If the rays of light coming from a farther light source reflected to any point on axis of the concave mirror, they form concentric circles at that point. When it is supposed that the sun as a further light source, the eye of viewer as a point on the axis of a mirror, and a cloud as a reflecting surface, then it can be observed the concentric circles are forming on the axis. He was not able to verify this because his theory that light from the sun is reflected by a cloud before reaching the eye did not allow for a possible experimental verification. This explanation was repeated by Berlioz, and though incorrect, provided the groundwork for the correct explanations later given by Kamal el-Din al-Farisi in 1309, and independently by Theodoric of Freiburg, c. 1250, c. 1311, both having studied at Al-Haytham's Book of Optics. Ibn al-Haytham's contemporary, the Persian philosopher and polymath Ibn Sina, Avicenna 980 through 1037, providing an alternative explanation, writing that the bow is not formed in the dark cloud, but rather in the very thin mist lying between the cloud and the sun or observer. The cloud, he thought, serves simply as the background of this thin substance, much as a quicksilver lining is placed under upon the rear surface of the glass in a mirror. IBN Sina would change the place now only of the bow, but also the color formation, holding the iridescence to be merely a subjective sensation in the eye. This explanation, however, was also incorrect. IBN Sina's account accepts many of Aristotle's arguments on the rainbow. In Song Dynasty China, 960 through 1279, a polymath scholar official named Shin Kuo, 1031 through 1095, hypothesized as a certain Sun Xingong 1015 through 1076 did before him that rainbows were formed by a phenomenon of sunlight encountering droplets of rain in the air. Paul Dong writes that Shen's explanation of the rainbow as a phenomenon of atmospheric refraction is basically in accord with modern scientific principles. According to Nazar el-Biziri, the Persian astronomer Qutb al-Shirazi 1236 to 1311 gave a fairly accurate explanation for the rainbow phenomenon. This was elaborated on by his student Kamal al-Din al-Farisi 1267 through 1319, who gave a more mathematically satisfactory explanation of the rainbow. He proposed a model where the ray of light from the sun was refracted twice by a water droplet, one or more refractions occurring between the two refractions. Re- one or more reflections occurring between the two refractions. An experiment with a water-filled glass sphere was conducted, and El-Farazi showed the additional refractions due to the glass could be ignored in his model. As he noted in his Kitab Tanquil al-Manaziri, the revision of the optics, Al-Farazi used a large clear vessel glass in the shape of a sphere, which was filled with water, in order to have an experimental large-scale model of a raindrop. He then placed this model with a camera obscura that has a controlled aperture aperture for the introduction of light. He projected light onto the sphere and ultimately produced through several trials and detailed observations of reflections and refractions of light that the colors of the rainbow are phenomena of the disposition of light. In Europe, Ibn al-Haytham's book of optics was translated into Latin and studied by Robert Grosseteste. His work on light was continued by Roger Bacon, who wrote in his Opus Majus of 1268 about experiments with light shining through crystals and water droplets, showing the colors of the rainbow. In addition, Bacon was the first to calculate the angular size of the rainbow. He stated that the rainbow submitted not appear higher than 42% above the horizon. Theodoric Theodoric of Frisberg is known to have given an accurate theoretical explanation of both the primary and secondary rainbows in 1307. He explained the primary rainbow, noting that when sunlight falls on individual drops of moisture, the rays undergo two refractions upon ingress and ingress, and one reflection at the back of the drop before transmission in the eye of the observer. He explained the secondary rainbow through similar analysis involving two refractions and two reflections. Descartes' 1637 treatise Discourse on Method further advanced this explanation, knowing that the size of raindrops did not appear to affect the observed rainbow. His experimented he experimented with passing rays of light through a large glass sphere filled with water. By measuring the angles that the rays emerged, he concluded that the primary bow was caused by a single internal reflection inside the raindrop, and that a secondary bow would be caused by two internal reflections. His he proposed this conclusion with a derivation of the law of refraction subsequently to but independently of Snell, and correctly calculated the angles for both bows. His explanation of the colors, however, was based on a mechanical version of the traditional theory that colors were produced by a modification of white light. Isaac Newton demonstrated the white light was composed of the light of all the colors of the rainbow, which a glass prism could separate into the full spectrum of colors, rejecting the theory that the colors were produced by modification of white light. He also showed that red light is refracted less than blue light, which led to the first scientific explanation of the major features of the rainbow. Newton's corpuscular theory of light was unable to explain supernumerary rainbows, and a satisfactory explanation was not found until Thomas Young realized that light behaves as a wave under certain conditions and can interfere with itself. Young's work was refined in the 1820s by George Biddle Airy, who explained the dependence of strength of the colors of the rainbows on the size of water droplets. Modern physical descriptions of a rainbow are based on my scattering work published by Gustav V. Me in 1908. Advances in computational methods and optical theory continue to lead to a fuller understanding of rainbows. For example, Nussensweg provides a modern overview. Experiments. Experiments on the rainbow phenomenon using artificial raindrops. Example, water-filled spherical flasks go back at least to Theodoric of Frisberg in the 14th century. Later, also Descartes studied the phenomenon using a Florence flask. A flask experiment known as Florence rainbow is still often used today as an imposing and intuitively accessible demonstration experiment of the rainbow phenomenon. It consists in illuminating with parallel white light and water-filled spherical flash through a hole in a screen. A rainbow will then appear thrown back, projected on the screen, provided the screen is large enough due to the infinite wall thickness and the macroscopic character of the artificial raindrop. Several subtle differences exist as compared to the material phenomenon, including slightly changed rainbow angles and a splitting of the rainbow orders. A very similar experiment consists in using a cylindrical glass vessel filled with water or solid transparent cylinder and illuminated either parallel to the circular base. Example, light rays remaining at a fixed height while they transit the cylinder, or under an angle to the base. Under these latter conditions, the rainbow angles change relative to the natural phenomenon, since the effective index of refraction of water changes. Bravurius index of refraction for inclined rays applies. Other experiments use small liquid drops. See text above. Culture. Rainbows occurred frequently in mythology and have been used in the arts. One of the earliest literary occurrences of rainbow in the book is in the book of Genesis, chapter 9, as part of the flood story of Noah, where it is a sign of God's covenant to never destroy all life on earth with a global flood again. In Norse mythology, the rainbow bridge Bifrost connects the world of man, Midgard, and the realm of the gods, Asgard. Michiveria was the god of the rainbow of the Muisca in present-day Colombia, and when the regular rains in the Bogota savanna were over, the people thanked him, offering gold, snails, and small emeralds. The Irish Leprechauns' secret hiding place to his pot of gold is usually said to be at the end of the rainbow. This place is appropriately impossible to reach because a rainbow is an optical effect which cannot be approached. Rainbows sometimes appear in heraldry too, even if a characteristic of multiple colors doesn't really fit into the usual heraldic style. Rainbow flags have been used for centuries. It was a symbol of the corporate movement in the German Peasants' War in the 16th century, of peace in Italy, and a gay pride and LGBT social movement since the 1970s. In 1994, Archbishop Desmond Tutu and President Nelson Mandela described nearly democratic post apartheid South Africa as a rainbow nation. The rainbow has also been used in technology product logos, including the Apple computer logo. Many political alliances spanning multiple political parties have called themselves a rainbow coalition. 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 Rainbow from Wikipedia, the free encyclopedia.